In this lesson, we are going to work with a periodic table. The periodic table it has a lot of importance because knowing how the elements are placed in the periodic table, we can get a lot of information, mainly qualitative information, it's true, but it can help us to predict, in many cases, the behavior or some of the properties of the materials. Of course, materials are made up of atoms, you know. Then we will start by solving two very simple exercises to review some very basic things, very basic, well-known concepts that all of you surely know. First, we are going to calculate how many atoms are in 100 grams of silver. We know that 1 mole of any substance contains a number of atoms which is equal to Avogadro's number. Yeah? We need to know the mass of 1 mole of silver. By looking at the periodic table, then we see that the atomic mass of silver is written here 107.868 grams per mole. 1 mole of silver weighs this amount, so that means 6.023 10 to 23 silver atoms weigh this amount. That's the definition of a mole. So 1 atom of silver weighs simply m sub w divided by Avogadro's number. We divide, and then we know that in 100 grams of silver there are 5.58 10 to 23 atoms. Yeah, quite simple, quite known. Another example is suggested here. Scientists are considering using magnetic alloy nanoparticles as a very high density data storage medium. One of the alloys that could be used is iron platinum. With arrangement of such nanoparticles, trillions of data bits per square centimeter could be achieved. This figure is between 10 and 100 times that of a hard disk. Now the question: if 3 nanometer diameter iron particles were used, how many iron atoms would there be in each nanoparticle? For the sake of simplicity, we are going to assume that we have particles spherical in shape. 3 nanometers diameter, that means 1.5 nanometers in radius. Depending on the data, provided in the statement, we can follow different approaches. Here, there is no single route. In this case, we are going to suppose that we have only the periodic table because we are trying to bring forward the big importance of the periodic table. So let's assume that the only thing we have is the periodic table. Then we can look for some values, some figures, some properties, and in particular we can see the density and the atomic weight of the element in which we are interested on now, which is iron. And then we'll calculate the volume from the radius, it's given in the statement, and we'll try to determine the mass and the number of atoms. So first we need to determine the mass of the nanoparticle. We have the radius or the diameter, then we have the volume, we have the density, then we have the mass. Volume is spherical, we have assumed spherical, so 4/3 pi r3. Put the numbers here, and this is the volume we obtain. Mass is equals density times volume. Substitute the figures here, and it's the value we obtain for the mass. And now we need to calculate the number of atoms. Again, we must look for the Avogadro's number. It's again the same. Now we don't know the value of this m, but we have the periodic table on hand, and then 55.847 grams per mole. Um, this is a human hair. This is a human hair magnified about 200 times. The diameter of one hair is of the order of 100 microns. Iron particles about 10 microns in diameter are sometimes used in breakfast, in the cereals for breakfast, or in vitamin tablets. These 10 micrometers particles are about 10 times smaller than the human hair. Yeah. How many iron atoms are in one of these particles? That's for you. That's an exercise for you. Okay, here I left an exercise for you. We want to coat a piece of steel that has a surface area of 1,250 square centimeters with a nickel layer, a thin nickel layer of 5 to 10 to minus 3 centimeters thick. It's not very useful, but we want to know the number of nickel atoms needed to prepare this coating. So how many atoms are there? From a practical point of view, it would be perhaps more useful to now not the number of atoms. We're not going to count atoms, but the number of moles. So how many moles do represent this the amount of atoms you have calculated? And finally, if you want to go to buy the nickel to a shop, then you are going to ask for grams of nickel or kilograms of nickel or whatever, and not for moles. So how many grams of nickel would be needed to this approach? Okay, we have been talking about the different scales in the structure. First scale, if you remember, is subatomic scale. In the subatomic scale, what we are going to consider is how the electrons are placed or are arranged to form the atoms, different atoms. As you know, an atom consists of electrons, protons, and neutrons. So we are going to see more. Okay, normally protons and neutrons, of course, are in the nucleus. We are going to consider how the electrons are arranged because it's the particles that in the part of materials or the field of materials we are more interested on. Electrons, as you know, occupy discrete levels, and the positions of these energy levels are characteristics of each atom. And this is very important because the position of these energy levels is a fingerprint. There are no two atoms having the same scheme or the same positions for their energy levels. And that will be very important in many applications. So each energy level is identified, that's something also you know, by 4 quantum numbers. The principal quantum numbers N identifies the clustering cells, so it indicates the rough or the roughest level. And then we have the azimuthal or orbital quantum numbers, which are orbital, magnetic, and spin angular momentum, and that will identify the final shape of the orbitals within each cell. That means we will see later that within any of these cells, within these cells, we can have different levels or different sub-levels. These different sub-levels are being identified by these 3 quantum numbers: magnetic, spin, and orbital. For instance, here you have a p level. A p level can accommodate up to 6 electrons with a maximum of 2 in each sub-level, each orbital, according to the Pauli exclusion principle. Let's remind the quantum numbers NLMS, you know, so it's nothing new. N is the principal quantum number. As told, it identifies the shell in which the electrons are placed. They are integers, and in addition, its cortex or its cell is identified with a letter: K for N1, L for N2, M for N3, and so on. And these letters are used to identify the cells in different spectroscopic techniques. Yeah, as told, the position of the different cells its characteristic is a fingerprint of the atom. It's exclusive of each atom. It's going to be a very useful tool to identify and to determine the composition of the materials. Then we go to the number of energy levels in each of these cells. The number of orbitals inside within any of these cells, which are defined by, this number is defined by two quantum numbers. The orbital quantum number, angular momentum, determines the number of orbitals for each level. It takes values from 0 to n-1 and determines the shape of the orbital. Determines whether it's spherical for L equals 0, or it's elliptical, or has different strange shapes you will see later. But within each of these orbitals, the value of the magnetic quantum number will indicate the number of suborbitals within each orbital. And the range is from -L to +L. Therefore, for each L orbital, there may be up to 2 times L plus 1 suborbitals. Finally, spin. The spin angular momentum will indicate the direction of the spin of each of the electrons in the same orbital, or in the same suborbital. I mean, each suborbital can accommodate maximum 2 electrons, one rotating rightwards, the other leftwards. So the two spin signs. And the value is ±1/2. Let's go back to the periodic table to see a couple of examples of how these quantum numbers are used to determine or to illustrate the electronic structure of atoms. We consider first calcium. Calcium is placed here in this column of the periodic table, and the structure is 1s2, 2s2, p6, 3s2, p6, 4s2. Okay, it has 4 cells, n from 1 to 4. N equals 1 has a single orbital. The only possibility is L equals 0, so we have an s orbital. N 2, 3 have 4 orbitals each. So S for L equals 0 and P for L equals 1, and in each case 2 electrons in each orbital, hence 2 in 6 and 6 in P. That correspond to magnetic moment -1, 0, 1, and then we have 2 electrons with antiparallel spin ±1/2. For n equals 4, only we have 2 electrons, because we have only 2 electrons left. Then they will occupy the lowest possible orbital, which is the orbital s. Another case, here we have palladium. Palladium is in the transition metals, so it's a more complicated structure, because then, as you know, here the d shell is beginning to fill. So here we have 1 orbital, n1, n1, n2, n3, n4, n5, and when we fill the shell for n3, then we see here that we have the d orbital. So it has 5 cells, n 1 to 5. Again, n equals 1 has a single orbital, n equals 2, 3 have 4 orbitals each. So S for L equals 0 and P for L equals 1. Again, 2 electrons in each, 2 and 6 in P. And then the same for the angular momentum, magnetic momentum, and the spin. N equals 3 for the orbitals. L2 begin to be occupied, it's the d orbital. It can have 5 orbitals with L ranging from -2 to 2, so -2, -1, 0, 1, and 2, and 2 electrons with antiparallel spin plus and -1/2, hence a maximum of 10. For n equals 5, we have only 2 electrons. Then again, they will occupy the lowest orbital, which is the s orbital. Yeah? We have linear reviewing quantum numbers and electronic configurations because the importance they have, because of the importance they have on the many of the characteristics, many of the properties of the bond that different atoms can present, can form, and therefore they have a great influence on the properties of the materials. That's what really concerns us. One important, it's a mnemotechnic rule really, is the Aufbau principle, surely you know, and it's a graphic scheme or a graphic routine that allows us to determine in what order the electronic levels are going to be filled. Okay, this is to, sorry, I couldn't find the cursor. Here, this is the order, so first 1s, then 2s, 2p, 3s, then 3p, 4s, then we come to 3d, 4p, 5s, and etc. and so on and so on. This order of filling is not always exact. I mean, in most cases, it's true. It's a quite good mnemotechnic rule, but in some cases, the d and f orbitals, sometimes also p and d orbitals, but normally d and f orbitals are so close one to each other that sometimes are interchanged. Sometimes the filling order is not that one used here in this scheme, in this routine, but somehow they are something changed, somehow they are disordered. And so at the first sight, the configuration, the electronic configuration, the electronic terms appear to be disordered. That could, we could think that this is irrelevant, but the idea is that these anomalies can lead to very important properties in the materials. And just to give a couple of examples, these could give rise to the existence of different valence states. Then, for instance, the idea that copper oxide, you have many different copper oxides, and so the only difference between them is the valence state of copper. And also, a lot of magnetic effects could appear that were could be impossible without this appearance of unpaired electrons. Just to give you a couple of examples, I have here palladium and copper. In the case of palladium both are transition metals. In the case of palladium, the predicted, so to say, if we follow the Aufbau principle, the Aufbau routine, the predicted electronic structure would be 1s2, 2s2, p6, 3s2, p6, d10, 4s2, p6, d8, 5s2. Yeah? However, what happened is that because and that's so because first we are filling the 4d and then the 5p. First is 5s and then 4d. However, what happened is that in some cases the structure is 1s2, 2s2, p6, 3s2, p6, d10, 4s2, p6, d10. So what happened here is that these two electrons, so to say, jump back to the d level, and completely fill this d level. Now in this d level, this 5s should be filled before the 4d. Yeah, so it's disordered somehow, but this is more stable configuration. In the case of copper, something similar. 1s2, so we fill one shell, 2s, 2p3s, 3p4s, then we come to 3p4s, 3d. We can fill 3p, but 4s should be already filled, then 3d, so that means that we have this part here, 3s2, p6, d9, 4s2. However, the most stable configuration is not this one, but one of the electrons in this field, in this cell, in this 4s2 level, one of the electrons jumps back to the d level, so that the 3d level is fully filled before the level 4s has filled. Again, we have here an anomaly because 4s should be filled before beginning to fill the 3d, but again, this is the most stable configuration for this material, or for this element. Well, you see here what I was telling you about the levels which are too close. So here you see some levels which are really very, very close, so some interchange, some change between them could occur without any problem giving rise to. Okay, as we go from atoms to materials, as we go from isolated atoms to atoms building up a crystal material, new concepts begin to appear. And some of these concepts, most of them you already know, will be very important, will be of great relevance for the properties of the materials we will be concerned with. So one of the first concepts is the valence. Valence is the number of electrons that participate in the bond. Normally, they are electrons from the outer s and p orbitals, or p orbitals. And for instance, here I have a few examples. For magnesium, 3s2, so valence 2. For aluminum, we have electronic structure which is 3s2p1, then the valence is 3, and for silicon 3s2p2 and the valence is 4. Another important concept that will be quite relevant is electronegativity. Electronegativity describes the tendency of an atom to gain an electron to complete the last cell. You know that the most somehow stable configuration for an atom is to is to have all the cells as filled as possible, because that energetically is more favorable. For instance, in the case of potassium has 19 electrons, so 2, 4, 10, 12, 18, 19 electrons. It has 1 electron in the outermost cell, 4s1. That is, the tendency of this atom to lose the electron is quite high. I mean, it has, as soon as they can, these atoms are going to lose this extra electron that somehow is. So the electronegativity is very low, because the tendency is not to catch more electrons, but to lose the extra electrons, the extra electrons they have. The opposite is with chlorine, for instance. Chlorine has 17 electrons. So in the last cell, it's 3s2p5. Then we have 5 electrons in the last cell. So that means that we need 1 additional electron to fill this layer. The tendency to catch this electron is very high. Then electronegativity is very high also. And then it's somehow reflected in this atomic stability. In the same examples, potassium, it was 1s2, 2s2, s3, p6, 3s2, p6, 4s1. So 19 electrons, but the easiest is that this electron is lost. Then we come to the configuration of a cation, in which the last cell, 3s2p6, is the same as that of argon, which is the neutral atom, the neutral noble gas. In the case of chlorine, we had 17 p5 in the last cell. So as told, the easiest is to catch an additional electron. Then we come to this structure in which we have 3s2p6, again the same structure as we had for argon, but now with an anion. Okay, what does it mean for an electron to be in an s or a p orbital? Okay, you know from the uncertainty principle that we must delta x times delta p must be greater or equal to Planck's constant divided by 4 pi. When we are in this scheme, when we are in this quantum theory, or this, then we are considering electron as a wave, no longer as a single particle, but with a dual nature. So it's either a particle or a wave. And as a wave, the position is no longer a point in the space, but must change we must switch to talk about the probability for the electron to be found at one point or one region of the space. In this scheme, in this description, the orbitals are actually the eigenfunctions of the Schrödinger equation. We will come to it later, and the energy of each of these levels will be the corresponding eigenvalue. Okay, this is illustrated here. Here we have for the 1s, we have only a maximum. So here we have the maximum probability to find the electron in this orbital with s. If we go to s, then we have 2 points or 2 regions, 2 maxima, in which the probability to find the electron is the maximum, corresponds to this orbital here and this orbital here. Here you have the corresponding wave function, and for 3s, again we have one level here, one level here, one level here. That corresponds to the 3 maximum, in which or 3 points, 3 regions in which the probability to find the electron is is maximum. You have here this scheme you know quite well, the different levels and how many wave functions are associated to any of these energy levels with all the quantum numbers represented here. Finally, also coming back to the shape of the orbitals, we have told that the s orbitals are spherical. You have seen two slides in the previous slides how the shape of the s orbitals was spherical. In the case of p orbitals, they are more elliptical, and there, so to say, there are two lobes, more or less elliptical lobes, that are symmetrical with respect to one of the axes, zeta for px, or here y, this is px, this is py, this is p zeta. So you have here the different symmetries reflected, and if you go to the orbitals are a little bit more complex. So you have here the xy, the xz, the yz. In this case, there is no the symmetry is not across one of the axes, but across the different planes. Again, here you have this into the orbitals. We have 5 different the orbitals. And of course, the extension of the orbitals grows with n. You have seen it in the former slide when you have a small region for S1s, then bigger for 2s, and then bigger for 3s. Electrons, as you know, can occupy the entire orbital, so electrons can be found anywhere here, anywhere here. This is because the orbital is constituted by the 2 lobes, or the 4 lobes in this case. And also very important is that the shape is going to determine how good or how strongly the bonds are formed. Yeah? And the periodic table still contains a lot of valuable information. It has so many valuable information that you can even describe the Marvel characters, or the Simpsons, or the fruits, or the Asterix characters, or whatever. Yeah, but this information is not so relevant for us as the fact that the atoms are not, or the elements in the periodic table are, of course, not randomly placed. Therefore, we can ask ourselves whether analyzing the trends of certain parameters, whether analyzing the trends of some properties along or across the periodic table, either along a column or along a row, could reveal some tendency that allows us to predict, at least qualitatively, the behavior of the elements. Well, for instance, here I have selected this column, this group. Is the group of carbon, silicon, germanium, tin, lead. carbon. Carbon in its diamonotropic form has a melting temperature over 3000 degrees. As we go down, then the melting temperature decreases. And so finally we come to tin or lead. In the case of tin, temperature drops to a little above, slightly above 200 Celsius degrees or 300 Celsius degrees in the case of lead. Yeah, of course, you see here you could say me, okay, here is decreasing the temperature, here decreases again, but here increases. Sure, I'm talking about quite general tendencies, quite general trends. So it's not a mathematical approach. Just you can more or less predict what is going on. But from here to here, the difference is extremely high, extremely large. In agreement with these differences in the temperature, in melting temperature, we could go for the band gap. If we look at the band gap, then we see diamond. In the case of diamond, forbidden gap is very large. It's around 6 electron volts. It's highly insulated and it's transparent. Silicon has only 1.1 electron volt. Germanium only 0.67, and tin and lead are metals. Therefore, no band gap at all. And in the table, in the graphs here, you have some other examples about, for instance, here melting temperature and linear thermal expansion coefficient, and you have represented here for the for all elements in the carbon group alpha thermal expansion, linear thermal expansion coefficient, melting temperature, and the band gap in the cases in which we have a band gap. Graphite is considered not to have a band gap, and of course tin and lead also not, since they are metals. And you see here the tendency as the zeta, the number of atomic number increases. And here again, because we had begun with this example, the big difference between the two allotropic forms of carbon, graphite and diamond, and the only reason is the different kind of bond. Okay? We have represented here the evolution of the melting temperature as a function of, or not as a function because it's not a real function, but versus the atomic number for these elements here. Yeah? Let's see how it's the evolution of these materials, not moving through a column as we have done before, but moving along a row. Now we consider, for instance, here, as you see, it's for this row here, so the melting temperature, even if we are quite close, but first increases and then decreases. Here are more separated and it's much easier to see. So here in this group, first temperature increases and then decreases. And here we have an anomaly. And now we are talking about general trends, not about mathematical formulas. And finally, in this third row, on the third row, we have the highest melting temperatures. Then again, you see the same tendency. It goes up, more or less to the mid part of the row, and then decreases again to reach, for instance, in this case, nickel, which is one of the metals with a low melting temperature. And now I leave an exercise for you. For elements in this group we have analyzing, plot the melting temperature. It's done for the same elements. Calculate and see the trends of the ionicity percentages of the corresponding oxides. What happened with the multivalence elements. In which case would you expect a higher modulus of elasticity? What is the modulus of elasticity and why? Some conclusion, and here you have a lot of information. Now it's your time.